Okay, so the first order of business is the email that was sent out for this said the time was 4:30 Eastern time, and the future talks in the series will go back to the old time, which is going to be 4 o'clock Eastern time. So the website has been updated for the talk in February, and future talks will be back at on the hour. But I'm glad all of you are here because when I joined on the hour, there was nobody, so this is much better attendance than 30 minutes before. Okay, so our speaker is Professor Evan Schneider, who is at the University of Pittsburgh. She specializes in computational astrophysics, focusing on galaxy evolution and numerical methodology. I've known Evan for a while because she was a graduate student at the University of Arizona, and has gone on to have prize fellowships and is now assistant professor. I assume, just based on the timeline, soon to be promoted professor at Pittsburgh, and is going to talk to us all about galaxy evolution and the exciting work that she's doing. So Evan, do you want to take it away?
Awesome. Yeah, thank you, Erica. Thank you for the introduction, and thank you for for inviting me to give this talk. Everyone can see my slides. Looks okay. Cool.
Yes.
Yeah, so in sort of thinking about what to talk about today, decided to actually kind of do a mashup of a couple of different projects I'm working on. But hopefully I've done this in a way that's coherent enough that you'll think as I do, that they kind of flow together by the end of the talk. And so this is primarily work that I've been doing with graduate student and postdoc collaborators here at the University of Pittsburgh. As well as, several collaborators, some of whom I think are on the Zoom at other institutions, who, it's been a real pleasure to work on these things with. All right, so I know that this is a pretty narrow group in terms of sort of topic focus, so I'm not going to spend too much time in the way of introduction. But I will just sort of spend a couple of minutes trying to motivate why I pursued some of this work. So first, even as a theorist, I always think it's appropriate to motivate one's talk with observations. So this is, my personal favorite composite of M82, right, the nearby starburst galaxy. It's one of my favorites because I think it does a really great job of highlighting the sort of multi-phase structure in the outflow, right? In particular, because we've got X-ray data from Chandra in this image. You can see in the very center of this edge-on, star-forming disk, there's this very hot, right? Very hot, meaning 10 million Kelvin or above, X-ray emitting plasma, right? That's being generated by all of the supernova explosions taking place at the center of the galaxy, which, as it moves out, the blue here is showing you sort of slightly cooler million Kelvin or so gas. And then embedded within that, right, there's all of these cooler clumps. So 10 to the 4 Kelvin clumps of gas and dust that are sort of spatially coincident with the hot phases of the outflow. And so this is a complex ecosystem. If I were giving a slightly different talk, I would spend a lot of time talking about why it's so important that we understand, how this process of, supernova explosions driving gas out of galaxies works. In this case, I actually want to focus more just on the properties of the gas in this system itself. But I will, sort of highlight the fact that one thing that we see, and that is, I hope evident to you in this image, is that there's a ton of structure, right? In particular, this is a galaxy scale composite, right? But you can see just by eye that there's structure in this system all the way down to sort of basically the pixel scale of the images, right? In particular, in these sort of cool clouds. And, in some ways, that poses a bit of a challenge for us, right? Because I'm a simulator, right? I like to try to make models of these kinds of systems, as do many other people. And in, typical simulator fashion, if I wanna model this system, what am I gonna do? I'm just gonna plop a grid down over it, right? And then sort of look at average properties of the fluid in each cell in my computational volume, right? And so, assuming that, this is a sort of typically resolved halo in a typical cosmological simulation, right? That means that instead of this very detailed structured picture, right, I'm going to get something much blurrier, right? Something like this. With apologies to all of the people doing, zooms in this room. But I will say, by the time you get out to the outskirts of this image, right, 10 kiloparsecs or so above and below the disk, this is not a totally unfair representation of sort of the typical resolution. And so one of the things I've spent a lot of time thinking about over the last few years is sort of, if we're doing this, right, if we have to do this by necessity in many cases, right, what are we getting wrong in this picture? And in particular, I've spent some time thinking about how, we can connect our numerical models to observations in this space, right, and help to sort of answer that question, and ideally then sort of back out some of the physics in this kind of system and others. So I'm going to start by talking about some of the work that I did kind of beginning as a postdoc, but also have continued over the last couple of years, which gets at this problem by just trying to sort of basically throw resolution at it, right? Say, okay, well, what if we actually just do the best that we can? We take the sort of all of the computational resources we can muster, and throw it at a system that looks like this, right? And try to actually just physically resolve the sort of cloud scale structure in one of these outflows. So that was the motivation behind this project. So the Choya Galactic Outflow Simulations, or Seagulls project, is a series of simulations that were all designed to kind of explore this particular question, right? What is happening in the sort of outflows from galaxies in particular? What's going on as you sort of mix the hot and cool phases, and trying to really sort of resolve, especially that cool phase structure. So our sort of fiducial set of models is sort of based on M82 in terms of the kind of size of the galaxy, right? So this schematic here on the right kind of shows you the overall size of the volume. It's roughly 10 by 10 by 20 kiloparsecs on a side. And the main advantage that we have in these models is indeed numerical resolution. So we run these on a fixed grid, and each simulation has kind of the same sort of number of cells as a typical cosmological simulation, right? So that gives us a sort of physical resolution across the whole domain of about 5 parsecs. Which is, enough to start to get at this question of what the sort of small scale structure actually looks like. The reason we're able to do that is because we're using this tool, right? So these days, hearing about GPU-enabled codes isn't actually as novel as it used to be, but this was one of the pieces of work that I started back at Arizona. So I just wanted to flash this slide up to let you all know that this is still an ongoing development effort. So Choya is the name of the code that we used, stands for Computational Hydrodynamics on Parallel Architectures, right? So the parallel is the reference to the GPUs here. And it's an open source fluid dynamics code that is developed for astrophysics simulations. So it's not just me developing it anymore. There have been a lot of contributions from other graduate students and other people that I've worked with, and I've tried to highlight here just some of the features that we have. Much of which, as I said, is the work of students and collaborators as well as my own. So back to Seagulls. Just a little bit more to kind of set the stage for the simulations I'm going to show you. These simulations, basically we initialize a sort of 10 to the 4 Kelvin gas disk that's rotating and in hydrostatic equilibrium in the vertical direction, with a sort of gas mass 2.5 times 10 to the 9. Solar mass is something like what M82 likely has. We embed that in a static potential, so we don't run the simulations long enough to expect much evolution in the disk or halo potential. And then we apply by hand supernova feedback in the disk. So I'll describe that a little bit more in the next slide. But it's worth noting that our supernova feedback is effectively resolved in the sense that we don't have to worry about, accidentally cooling away, radiating away a lot of the energy that's injected into the disk. So we sort of trust the outflow properties that come out because we don't employ a subgrid model to do the actual feedback injection. In these simulations I'm going to show today, we don't have a star formation model or a cold ISM phase. That's something that we are working on and have a sort of upcoming set of simulations where we've included those elements. So I mentioned I would say a little bit more about the feedback model, just so you have a handle on kind of what we're doing. Basically, we assume that stars are forming in clusters, and so we're going to distribute the feedback in a clustered fashion. And so clusters in our model are just the sites where we're going to inject mass and energy, right? So they have a size that means that they're resolved by many cells in our computational domain. And we just inject mass and energy basically as a function of time based on a sort of single stellar population model. In this talk, I'm going to describe two different models that we used for the feedback distribution. So one is a central sort of burst model, something more like MAD2, a kind of nuclear starburst where everything is really concentrated in the center, more representative of what you see in kind of local starburst galaxies. And the second is what I'll call the distributed model. So clusters sort of sprinkled throughout the disk following basically the gas surface density. And that's maybe, a little bit more representative of sort of a high redshift starburst system where basically the whole disk is just rapidly forming stars. And so we can sort of set the star formation rate for our simulation by sort of turning on clusters in sequence to hit a target sort of amount of star formation. And so for these simulations that I'm going to show, we used a star formation rate of something like 20 solar masses per year. All right, so enough description. What does one of these simulations look like? So this is an example actually showing a movie of our distributed cluster model. And as you can see, basically you have the clusters kind of embedded within the disk, and as those clusters go off, I'll play it one more time. They drive gas out, right? So this is actually one of our low resolution simulations. It's hard to make a time resolved movie with like hundreds of terabytes of data, but you get the picture, right? So you sort of are driving gas out in this large scale outflow, and then we can investigate the properties of the gas in this system. All right, just to give you a sense of the difference between the models, I'm going to talk a lot in the next few slides about some differences between the sort of central burst or nuclear starburst model, which is the sort of Siegel's 4 simulation, versus the more distributed model, which is Siegel's 5. So this is just a projection, density weighted temperature projection through the domain for each of these. And you can see the central burst model on the left, the distributed burst model on the right. These have the same star formation rate, right? It's just how the clusters are distributed that varies. And you can see already, right, that the central model it drives this sort of hotter, faster outflow with less, obvious sort of cool gas, right? So looking at the distributed model on the right, all of the purple stuff, right? That's the cooler, denser gas that's kind of embedded in this background volume filling hot phase. So there are already significant differences, in the, sort of the large scale cool gas structure between these two models, just based on how the star formation is distributed. All right, so I want to show now a little bit more, quantitatively what some of the features of the simulation looks like and the outflow. So these are slices through the center of the computational domain, going from left to right. We have the density, the number density, the temperature, the the velocity, and the color, which is just a passive scalar that we advect with the fluid, which basically allows us to trace where the gas in the outflow came from, whether it was ISM material or material that was associated with a sort of cluster injection site. So these are also movies that I can play. And as you watch them, you'll get a sense for how this outflow sort of develops. And I'll say that, qualitatively, this simulation is very similar to the central burst. And it's only sort of quantitatively that we see differences. So over the course of 20 million years or so, this thing develops. And as you can see, right, it develops this characteristic structure. So lots of cool, dense clouds embedded in this sort of volume filling hot phase, where the velocities are strongly correlated with the phase, right? So the hottest regions are also the fastest moving, and then the cooler clouds are sort of embedded within them, moving out more slowly. I should say, if anyone has questions during the talk, you should just interrupt me or put them in the chat. I'll try to keep track.
Yeah, you can raise your hand or write them in the chat.
Yeah, cool. All right, so what can we learn from this? Before I move on to the sort of cloud scale structure, I want to just briefly mention the hot gas, because this is a talk about diffuse gas, right? And we learned a lot about how the hot gas in outflows behaves from these models. In particular, one of the main things we learned is that you can't ignore the sort of two-phase interaction if you want to sort of correctly predict the properties of the hot phase. And basically what that means is that, as the hot phase of these outflows is developing and moving out, it's constantly interacting with all of the small scale cloud structure, and that changes its thermodynamic properties significantly. So these are plots basically showing, in radial shells moving out, what the average properties of the hot phase gas are. So here I've just, made a temperature cut for anything above 5 × 10⁵ Kelvin. And I'm showing number density here in blue, temperature in red, pressure in yellow, and radial velocity in green as a function of spherical radius from the center of the galaxy. And the black lines on the first 3 of those plots are basically the prediction that you would make from a purely adiabatically expanding wind model, the Chevalier and Clegg type model, if you're familiar with those. And the main point is that the densities and the temperatures and the pressures are all significantly higher, and the profiles are significantly flatter in this model as a result of the interaction between the hot phase and the cool clouds. A sort of corollary to that is that the radial velocities, which do asymptote to a sort of characteristic value, in this simulation, that's somewhere between 800 and 1,000 kilometers per second, those are actually, a factor of 2 or more lower than what you would predict just based on the sort of energy and mass injection rate from the supernovae, again, as a result of their interaction with the cool phase. So that's partly because they transfer some momentum to the cool phase, but also partly because they just literally are shocking constantly against the cold clouds, which stalls the gas and converts some of that kinetic energy into thermal, which is part of the reason that the temperature profiles are also flatter. All right. Quick note, just because I can't help myself on some of the sort of results in terms of how much mass and energy you get out of galaxies in these models. So one thing that is true of these models is that if you look at the sort of nuclear burst version versus the distributed burst version, you do get, sort of quantitatively very different amounts of gas in different phases. So this is now just actually a radial plot of mass outflow rates, again, as a function of radius, but split up by phase. So blue being the sort of cool gas, green is an intermediate temperature phase, and red being the hot. Black is showing you the total. And so as you can see in the central burst model, basically at small radii, there's more outflowing mass in the cool gas. But as you continue to move out, the hot phase actually overtakes it. So you have more total gas moving out in the hot phase in that central burst model than in the cool phase. And in part, that actually is indicative of mass being transferred. So in that system, cool gas is actually getting destroyed as it's being carried out. And that destruction is mass loading the hot phase, which is why you actually see the hot phase outflow rates increasing as a function of radius. The distributed, right, it looks very different. You actually, have a lot more mass in the cool gas. And actually, this is maybe not necessarily a time constant curve, but at all radii, you have more mass outflowing in the cool phase. Although interestingly, these snapshots were taken for both simulations 30 million years after the sort of start of feedback, and they have very similar total mass outflow rates, at 5 kiloparsecs at that time, right? So both of these, if you're used to thinking of things in terms of mass loading factors, right, the outflow rate relative to the star formation rate in the system, these are mass loading factors of around 0.25, right? So less than unity, but of order unity. The energy that comes out looks really different between the two models. In particular, these plots are now showing energy outflow rates as a function of radial distance. And the dashed black line in each plot shows you what the sort of total available energy is based on the star formation rate, just assuming that every supernova, is 10 to the 51 ergs, and all of that energy is available to couple to the outflow. And so you can see that in the central case, in both cases, the majority of the energy is carried by the hot phase, not the cool phase. But in the central case, about 50% of the total available energy is actually getting out. This is a high specific energy outflow. That looks really different in the more distributed case. So in the more distributed case, by the time you get out to 5 kiloparsecs or so, you're looking at energy, energy loading factors of more like 5%. Comparable in the sort of cool gas phase. So a couple percent of the available energy is showing up in the cool phase in this simulation. And so that also, I think, is indicative of sort of like the way that the mixing happens. So in the distributed model, the hot gas spends more time as a function of volume as well, interacting with cool gas, right? Generating gas at sort of intermediate densities and temperatures, which is very susceptible to radiative cooling, right? And so that energy just basically gets radiated away as you continue to mix on your way out. Okay, so I wrote an abstract about clouds, so it's time that I get to talk about clouds. So one of the things that we did was we wanted to think a little bit more about what the actual structure of the cool gas in these models looked like. And so the way we did this was by generating a set of cloud catalogs for both of these simulations across many snapshots. And so in our definition, a cloud is basically just a contiguous set of cells that has a temperature less than 2 times 10 to the 4 Kelvin. So we do a temperature cut and then look for connected cells based on that temperature cut. And we store, a bunch of properties for each cloud, volume, mass, position, momentum, a sort of measure of the kinetic energy, et cetera. Just to give you a sort of sense of scale, each of our snapshots for each simulation has about 10 to the 5 clouds in it. And for the purposes of the next few slides, I'm going to consider a cloud to be resolved if the, sort of equivalent spherical radius, in other words, some of these clouds are elongated, but we can take the volume and divide it by, the number of cells to determine a sort of spherical radial equivalent. If that is larger than about 8 times the cell size. So that corresponds to something like 2,000 cells, or about 40 parsecs for our highest resolution simulations. All right, so what can we do with this? One of the things we can do is look at distributions of cloud properties. So now I'm showing on the left a histogram of just the number of clouds as a function of their size, that sort of spherical equivalent radius. And in all of these plots, the central burst model is going to be shown in orange, and the more distributed burst model is shown in black. One thing you can see right away is actually that these distributions look pretty similar. So one thing that this points to, and I'll make this point, more strongly in another slide or two, is that we think the properties of these clouds are more or less set by by turbulence in the system and in the outflow. And so turbulence makes sort of specific predictions for what the power law distributions should look like, which is one of the reasons I think that despite the fact that the outflow properties themselves are somewhat different between the two models, the sort of statistical properties of the clouds end up looking very similar. In terms of how much mass is there as a function of size, that's what the plot on the right is showing, and the gray dashed line is our sort of resolved limit. So I'll just say, the fact that we see a drop off in radius to the left of that line could be indicative of there being a physical mechanism that preferentially destroys clouds below some characteristic size, but it's also in this case certainly going to be an effect of the numerical resolution of the simulation. We just can't capture correctly the distributions below that sort of physical size scale. You may notice right in these plots that one major difference between the two simulations is that the distributed simulations has a few really massive clouds. And those actually are sort of outliers in the sense that they are clouds that are being fed kind of directly by the ISM. In other words, we have to make a cut right at some point to not include the ISM of the galaxy. But if we didn't make that cut, those clouds are actually sort of connected to the gas in the ISM. So they're continuously being fed via these sort of filamentary structures from the ISM. In that sense, they show up as outliers in these sort of statistical distributions, and their properties are not sort of set the same way. All right, one of the reasons I wanted to show these sizes is because it's related to a sort of theoretical question, I think, that has been raised in the community in recent years, which is whether or not you could actually, create more cool gas in winds, right? In other words, if you seed a population of cool clouds near the base of an outflow, can you actually grow those clouds as they're moving out by sapping mass from the hot phase? Right? This is a sort of reverse destruction process, right? For many years, we were kind of worried about how you could get cool gas out in hot outflows because, if clouds are small, they tend to be destroyed and just incorporated into the hot phase. But a series of sort of smaller, higher resolution simulations have shown that with a specific set of criteria, you can actually reverse that process. You can kind of mix material in from the hot gas, cool it efficiently onto the tails of these clouds as they're being carried out, and thereby kind of grow the cool phase in winds, which of course would have major implications for things like, what the observed cool gas content in winds means. And so we actually kind of looked at this in these simulations by examining where our clouds fell relative to the sort of critical size scale that some of these theoretical studies have suggested is the scale, that determines whether or not a cloud is going to grow or be destroyed in a wind, right? So this plot, which is now actually a plot just for the nuclear burst, the central burst simulation, is showing, a 2D histogram as a function of distance and cloud radius, right? So each of these bins tells you how much mass there is in clouds at that distance with that size, right? And then the blue and black lines are showing two of these theoretical predictions for the sort of critical size of a cloud in order to grow. And so the idea is that if you're above this line, cloud mass that's above this line should be able to grow in an outflow, and cloud mass that's below the line should be, on average, actually getting destroyed, right? Getting added into the hot phase. And so if we actually just focus on the smallest radii at first here for the central simulation, things below about 2 kiloparsecs, right? Which all clouds have to make it through whatever's happening at small radii, right? In order to get out to larger ones. One thing that we see is that the majority of cloud mass is actually in the destruction regime, right? In other words, these conditions are not favorable for cloud growth. As a result, we think that may be one of the reasons that we see relatively few large clouds, further out in the sort of central feedback simulation. On the other hand, this critical radius stays pretty flat. So if a cloud is able to survive, right, like these guys, it should continue to survive and grow. So in this simulation, we actually see that the largest clouds that are sort of driven out can survive. But because the majority of the mass is actually down here, and of course, even more of it is down here below our sort of resolved limit, so we can think about what that might mean. We don't see net cool gas growth in this outflow because, even though the biggest things can grow, there's still more mass in the smaller things, right? And so they're sort of subject to net destruction. The situation looks a little bit different in the distributed feedback case, right? Which I think is one of the reasons that at late times in those simulations, you saw a lot more cool gas, which is to say that at small radii, the outflow is more favorable to, to cool gas being able to grow. The critical radius is significantly smaller. And so you actually have a lot more of the mass winds up basically being above that threshold, right? And so as a result, I think this is part of the reason, right, we get some of these really big clouds in this simulation at larger distances. So another way of putting that, right, basically is that, more than half of the mass in the distributed simulation is in clouds that are consistently above the critical size threshold. So we don't necessarily see that net mass loss from the cool phase the way that we do in the nuclear burst simulation. That said, all of this, there's a caveat, which is that we can't really interpret any of these individual structures as clouds the way that the small scale simulations do. They really wind up being more like pattern structures in the outflow, where their actual sort of properties differ on small scales from on large scales. So even though they may be gaining mass, as a result of being large, they're also constantly sort of fragmenting, coagulating, moving with speeds that are different than the actual speed of the gas within them. So there's a lot of sort of subtleties there that make it a little bit difficult to compare directly from these simulations to the sort of smaller scale idealized simulations where these predictions come from. All right. So now I want to move on a little bit to talking about the mass distributions, because I think this is going to kind of lead into the second half of the talk. So this is just showing you a normalized, histogram of the cloud mass in both simulations. And, on the left is the sort of, as I said, like normalized PDF, and on the right is, mass per bin. And one thing we see in both simulations is that to like very high accuracy in the resolved portion of this histogram, the fit to this slope is precisely -2, which if you are familiar with sort of PDFs, mass PDFs, right, that basically means equal mass and equal bins, which is why you see, roughly flat slopes here on the right. And this is interesting because this is a slope that you expect to get from turbulent fragmentation, right? In other words, this is suggesting, as I said earlier, that the statistical properties of the clouds in these outflows are really being set by the turbulence in the system. That also indicates that, anything below the sort of, 10 solar mass-ish range where we start to fall off, is probably not numerically resolved, right? This is one of the reasons that I was saying that it's, it's hard to draw conclusions about things below that sort of size scale, because we see that it also breaks statistically. But over 4 orders of magnitude or so, we're able to demonstrate, a nearly perfect fit to this power law. And so, again, that's one reason we think we're capturing sort of, more than half of the total mass in these systems. Of course, these large clouds are outliers, right? And they don't match that same pattern. All right, so I wanted to talk a little bit about resolution because that does kind of lead into the next phase. So this is actually just, again, showing a temperature slice. On the left are 2 different resolutions for the nuclear outflow simulation. And then on the right, just for comparison, so you can get a sense of, model difference versus resolution difference, is the more distributed simulation. And so you can see there are definitely differences between our sort of 20 parsec resolution model and our 5 parsec resolution model. And the question is sort of, do those differences matter? And on what scales can we start to say that we're resolved or converged in certain properties? And so, one way of looking at this is to look at the sort of aggregate statistics. So these are the same radial plots, size plots for clouds that I was showing earlier. But now you can see them for all three resolutions in these simulations. So blue is our high resolution, sort of fiducial 5 parsec resolution. Green is the intermediate, and red is the largest. And not surprisingly, right, as you increase the resolution of the simulation, you start to resolve smaller and smaller scale structures, right? And so we see this distribution start to peak, the sort of peak of the distribution start to shift. That said, in both cases, the sort of maximum size scale that we see is the same, right? We don't get significantly larger structures in the lower resolution simulation than we get in the high resolution simulation. It's just that where the mass is gets redistributed. This funny break in the size distribution in the distributed simulation, I think may be real and may be related to that critical radius threshold that I was pointing out. Sort of basically clouds above this size scale can grow, clouds below this size scale tend to get destroyed. But we need to do a little bit more work before I'll believe this actual shape. Okay. Same kind of story for the mass distributions. In fact, we get the identical -2 power law for all of these simulations if we're measuring over the resolved mass range, right? Which is to say that for each of these models, that power law breaks at a higher mass. So again, that pointing towards this being a sort of universal structure function, right? But also the fact that you can't get it over very many orders of magnitude without going to quite high resolution in the model. All right, so that brings me into the sort of second thing I wanted to talk about, right? Which is that mass function, that -2 power law, may well be universal. Like I said, it's sort of predicted from turbulence. And people who have run turbulent box simulations, this is a series of simulations of clouds, cool clouds in turbulent boxes run by Max Gronke, find the same power law distribution. So in this particular set of simulations, it was showing that, again, above a critical size scale, clouds kind of survive in these turbulent boxes, and below that size scale, they tend to be destroyed. But also for the clouds that survive, you get this power law distribution of droplets, right? And that's really powerful because A, it means maybe we can predict small scale structure in simulations where we can't resolve it. But B, there should be, anytime you have large clouds, a lot of small clouds. The small clouds are going to have a large area covering fraction, right? In fact, they may be the thing that dominates observations of any system that's sort of cloudy like this, right? So these, I should say, I borrowed some of these slides from Kate Rubin, and I'm just using them totally shamelessly. So many thanks to Kate for letting me use some of the stuff she set up here. So these are just equivalent with distributions here, but as a function of physical separation between sightlines, right? And the point being that for many of these sort of quasar sightline studies where we're looking at equivalent widths, right? We may be dominated by sort of the small scale cloud structure in these observations, even if that small scale structure is being seeded by larger, more massive clouds. And of course, unfortunately, right, the size scale of those structures could be well below the resolution limit of even the sort of best halo scale simulations. So this is work done by Rahul Ramesh and Dylan Nelson, sort of really pushing the resolution limit in a cosmological zoom simulation. So this is from the Gibble suite, sort of Milky Way mass halos, where you can see in the right panel, right, as they increase the resolution, you get to smaller and smaller scale structures. But what I actually want to point out is this plot on the left, where they're showing, their sort of spatial resolution in cool gas as a function of galactic distance, for their fiducial kind of Gibble simulation in black. So still hundreds of parsecs, right? So when I said before that blurred image of M82, right, had a sort of faithful representation of the size scale in sort of cosmological zooms, this is what I mean, right? We're still talking about hundreds of resolution, hundreds of parsecs in terms of the spatial resolution. Just for reference, right? The Siegel simulations I was talking about are this box down here on the lower left. So high resolution, but we don't get to go out very far, right? But I actually think that this is not the end of the world. In other words, because that mass function tells us sort of how the mass is distributed as a function of scale, it's possible that in a simulation like this, we're actually capturing mostly where the mass is. We just need to account for the small scale structure in these clouds in order to sort of make accurate predictions for observables, right? Or back out actual physical characteristics of halos from observables, which is the main goal of the next sort of thing that I wanted to talk about, which is Cloudflex. So Cloudflex is a project that I worked on with Cameron Hummels and Kate Rubin and Drummond Fielding for the last couple of years. And it's basically a parametric model for sort of cloud structure that takes as a given that we're not necessarily going to be able to physically resolve in a simulation all of the smallest scale structures, but that we can parameterize them in a fashion that allows us to sort of account for how they may affect observables, right? So the idea is that we generate these cloud complexes or cloudlet complexes, where each complex is assembled mass of random sort of Monte Carlo selected cloudlets, and you can set a variety of parameters of these complexes, right? So this is a complex, so it's a spherical cloud complex with a total mass. This one I think has a total mass of 10 to the 6 solar masses, and a minimum size cloudlet of 10 solar masses, right? That might be representative of one of these structures from Max's turbulent box, right? For any given complex, we can set the masses and locations of the cloudlets just statistically using a mass PDF, right? Where again here the slope of this PDF, which is alpha, for our fiducial models, we set to -2. Or 2 if you don't include the negative. And then the distance similarly we can set to be sort of preferentially closer to the center, and then trailing off as you move out. We can initialize velocities for each of the little cloudlets, just based on a turbulent velocity field, with whatever power spectrum you want and whatever sort of normalization you want. And for now, we'll just assume that all of the cloudlets in the complex, that this thing is sort of in pressure equilibrium and all the cloudlets have the same number density and the same metallicity. And for the model I'm going to show you for now, we'll assume a sort of constant magnesium-2 ionization fraction. And then we can observe them, right? So the idea is you have a background quasar that is a sightline passing through one of these cloudlet complexes, and it can intersect many clouds, right? Especially if you have small minimum cloud masses, your composite, right, Voigt profile will be a bunch of individual clouds all lumped together, right? And that's especially true as you go to smaller and smaller cloudlet masses, that you can have many overlapping contributions in these profiles. All right, and so I just want to talk a little bit about what we did with this model, and then I'll try to leave some time for questions. So apologies if I go a little bit fast. But basically we wanted to see okay, what happens to the observables as you change various properties of these cloud complexes? So if this is a fiducial cloud complex with a minimum cloudlet mass of 10 solar masses, some number density 10 to the -2, a mass of 10 to the 6 solar masses, right, and a size of 5 kiloparsecs, right? If we change one thing, right, let's just change the minimum cloudlet mass. When we go to really small cloudlet masses, right, the sort of projected density shows you already that your areal covering fraction gets much larger, right? So as you increase the minimum cloudlet mass, right, your covering fraction gets smaller, right, until, at the largest cloudlet masses, you just have basically blobs. That said, all of these models have the same volume filling fraction, right? It's the same total amount of gas. You can then observe the complex, right? And so for the histograms I'm about to show, we observed each of these with, say 10 to the 4 background sightlines and put together, as many histograms as you want, basically, of different features, right? So, this is showing magnesium 2 column density as a function of minimum cloudlet mass. This is showing magnesium 2 equivalent width as a function of minimum cloudlet mass. Here, the minimum cloudlet masses are being shown in the, the color bars. And finally, covering fraction as a function of magnesium 2 equivalent width, right? For different cloudlet masses here on the right? And so this, rightmost one, of course, is the most sort of observationally targeted in the sense that this is the kind of thing that we can measure. I'll just quickly say, we can do this for all of the different parameters, right? So this is the same experiment, but now by changing the number density of the cloudlets, right? So going from very low number densities, more diffuse, bigger blobs on the left, to high number densities, denser nuggets on the right. One thing you may notice is that it has a sort of similar effect on the covering fraction equivalent width plot, right? And I'm showing that on purpose, right? Some of these parameters are degenerate, and I actually think that's a strength of the model. So for example, if you look now, just this top row is showing changing the total mass of a cloud complex. The bottom row is showing the total size. You can get very similar changes in the magnesium 2 equivalent width covering fraction plot by changing either one of those parameters, right? And as I said, I actually think that's a strength of the model because it means that if you're trying to figure out what your observations constrain, one thing, that this model allows us to do is sort of say like which parameters are degenerate with which, right? So in that sense, place more sort of confidence on those constraints. All right, I'll just very quickly show the application. This is all in the in the paper that we put out, so you can look at this in more detail if you want. But as a first application, we basically said, what if we filled a toy CGM with these cloud complexes and then observed it, right? Can we say anything based on current observational data about what the sort of cloud scale structure in the CGM looks like? So in this toy model, we have some mass distribution for the CGM as a function of radius. We assume some total mass. We assume, basically that the CGM is composed of these radial shells, each of which has a certain number of complexes in it based on the volume in the shell and the total mass in the CGM, right? From that, we can sort of pass a sight line through it, figure out the number of complexes that sight line should intersect. Going from there, right, we basically can make draws from our equivalent width PDF, right, for that sort of cloudlet cloud complex model, and add those draws up as you pass through individual complexes along the line of sight, right, to determine, what the sort of total equivalent width in that sight line should be. Doing that, right, now all of these draws we can place onto a sort of observationally motivated map, right? So this is magnesium 2 equivalent width as a function of, distance out in the halo, with some estimates from, observational surveys overplotted in the, the dashed and dash dotted lines, where the points here are the draws from our model. So this is for our fiducial model, minimum cloudlet mass of 10 solar masses, right? And you can see in some areas it's sort of statistically consistent with the observations, whereas, over here it's underpredicting, over here it's overpredicting, right? Again, for our sort of fiducial model, we can change the minimum cloudlet mass and see how that changes the distribution of draws relative to the the observational constraints, right? Some of these models are very clearly incompatible with the observations, right? In particular, when we raise the minimum cloudlet mass all the way up to 10 to the 5 solar masses, basically saying there's no small scale structure in these cloud structures, right? You get distributions that are totally incompatible with the observations. So skipping quickly through this, if you do this for all of the different sort of cloudlet complex models and different parameters that we varied, you can start to put constraints like, we can say, just based on this data, that for a 10 to the 10 solar mass CGM with our chosen metallicity, minimum cloudlet masses of larger than 100 solar masses, or number densities larger than 0.03 or smaller than 10 to the minus 3, total sort of complex masses larger than 10 to the 7, or sizes of the complexes smaller than 2 kiloparsecs. Those are inconsistent with observed distributions for magnesium 2 equivalent widths. All right, so in this plot, the gray bands are showing you the observed constraints, whereas the colored points are, each of our models, which is how we can say, okay, cloud complexes that are smaller than this are just not compatible with the observations. All right, so I'm actually going to just skip to the end now. I'll say the sort of link here, right, is that I think we can take halo scale simulations like Gibble and use them to inform, parametric models like Cloudflex, right, and put the two together. Basically, simulate the large scale and then mock up the small scale with Cloudflex to see what something like this halo would actually look like if you were able to resolve the small scale structure. And that's where I think we kind of need to go, because we're not going to be doing sort of Siegel's resolution models on halo scales anytime soon with current computational resources. So I'll leave my summary there. Apologies for going a little longer than I intended, and I'll take any questions.
Okay. Thank you, Evan. That was awesome. If you have a question, raise your hand. Carlos, you could go first.
Yeah, thanks, Evan. That was a really awesome talk. So sorry if I missed this, but going back to the Siegel stuff, if I understand right, you're just inputting clusters with an even distribution throughout the disk, and in the central model, you're clustering the clusters into the central region, right? So
yeah, more or less.
yeah. So I'm just wondering if there's, any treatment explicitly for like an AGN feedback component, or how that might, how might that differ from the central model?
Yeah, no, it's a great question. And it's definitely on my to-do list to just plug a simple AGN model into one of these simulations, because we don't have it right now. And yeah, so I think in some ways I can say, based on the difference between the sort of central model and the distributed model, like one thing I would definitely expect an AGN to do is sort of give you large scale hot gas features that are closer to the central model, right? It is, in effect, the most concentrated central model, right? So we don't have that right now. And I think it's definitely something that I have on my list to include. But based on the difference between those two models, if you're just concentrating the energy injection into a smaller and smaller region, right, that's kind of what I would expect it to do.
Okay. Ben Oppenheimer, question from you.
Yeah, Evan, great talk. I'll do a quick question. Have you looked, like you talk about turbulence, have you looked at vorticity in your simulations and measured that?
Oh, that's good. We didn't do vorticity. Do you mean the vorticity like of individual clouds or of the large scale outflow?
Where you can resolve it, basically. Yeah.
Yeah, no, that's a great idea. We looked at velocity structure functions, and actually something I didn't have time to show, but that I think is very cool is that like we can pick out the turbulent driving scale from the individual just first order velocity differences between the clouds, where it's a smaller scale for the central and larger scale for the distributed. But we haven't looked at vorticity. Is there like some particular reason that you mention it?
I just remember that that's a good way to like prove perhaps that the turbulence is driving the cool cloud formation and evolution. And I think I've seen papers do this a long time ago on very different scales.
Sure. Yeah. No, it's a great point.
Yeah.
That's something we should look at.
Yeah. Thanks.
Okay. David Ripke, go ahead.
Hi, Evan. This is Dave Rupke from, excuse me, Rhodes College in Memphis. We have some new observations of oxygen-6 in emission from a big galaxy where there's also an O2 nebula where we observe. So basically, we're seeing both the cool clouds and the cooling gas on very large scales. And I am trying to understand what this means in terms of cloud growth versus, clearly there's an interaction. So the morphology of these two, I'm happy to send you the submitted paper, which is not an archive yet, but it's basically we see the same morphology. So inferring that, we've got this cooling gas and sort of trying to figure out what the simulations are saying in terms of cooling. So it sounds like what your simulations find is that you're not seeing much cloud growth through this cooling process. We're looking at much larger scales and larger star formation rates, but I'm wondering if you could just say something about that and whether, sort of how generalizable you feel like your conclusion on cloud cooling is, cloud growth, I guess, through cooling.
Yeah, well, so one thing I'll say is that doing this exercise of comparing the two simulations, we did start to do a time series analysis. And I am not at all convinced that it's fair for us to consider this a steady state system. In other words, in particular in the distributed simulation case, this thing is still adding mass the whole time that we run the simulation. We run it for like 40 million years. And so what it looks like on larger scales 20 million years later, I think may be quite different. And in those conditions, right, if you've already got enough mass sort of above that critical radius threshold, maybe things do grow, right? I do feel confident that under certain circumstances, like the sort of M82 type parameters, you're not going to see a lot of cool gas growth. It's just not amenable to it. But in other systems, in particular these systems like the sort of higher redshift things where you've got more distribution of the star formation, you're just loading more cool gas into the outflow. I think over time that might change, right? But it's also tricky because then you're talking about, once you get to 50 million years, you're kind of talking about the kind of timescales of the starburst itself, at which point the feedback is gonna change and the hot phase properties will also change, and that could also contribute to sort of large scale cool gas growth. But yeah, I'd be very curious to see the results you have.
Okay. Can I ask a quick follow-up question based on something you just said?
Sure.
So you were comparing to M82, and M82 has this. The image you showed. There's also this PA image of M82 where there's dust there where it goes out. It's just this spray of emission, kind of filling the cones out to many kiloparsec. And I'm just wondering, is that sort of consistent with what you're seeing in terms of this model where the clouds aren't growing, they're shrinking?
Yeah, I do think, it's worth saying I was kind of harping on the cloud growth thing because that's, where we've spent a lot of our sort of theoretical resources in the last couple of years. But it's worth saying these models show quite clearly that you can definitely get cool gas out there, right? Which was a bit of a problem for a long time. So even if you're not adding to the flux on net, you're still, it's this is a really efficient mechanism to get cool gas out tens of kiloparsecs from the galaxy. And so I actually have a graduate student, Helena Ritchie, who's been working on M82 models with dust and kind of showing like what you can do. And it's in her models, like easily 50% of all of the dust that you put in the outflow makes it out. The question of pause itself is a little tricky because pause are very small. And so I think, I'll leave this for her paper, but probably you need some mechanism like shattering or something to kind of regenerate them as you move to larger distances. But it's no problem to get them out there, to get dust out there.
Thank you.
Okay, so we're just past the hour, but we have 2 questions left, if that's okay. Nicholas.
Yeah, I have question on the theory and then a question on observations, more comment. On the theory, in your Cloudflex model, did you include the kinematics to make the link to your first part of your talk when you model the outflow rates and stuff? Because that affects a lot how you add up the equation width to make the mock observations. And then the observation question is on the covering fractions. I think the covering fractions are known to be high in the center and low in the outskirts of the halo. So it's more important to look at the scale at which you have a 50% covering fraction rather than the average, because the average there is on some unknown distance.
Yeah. No, I completely agree. And I'll say we definitely made some simplifications, in the sort of first pass Cloudflex model. And, one of the goals is to do a better job, looking at lots of different observational probes. As for the theory question, we do have velocity structure, and that velocity structure is basically set by assuming that, these cloudlet complexes should have their own sort of internal velocity kinematics, and that those should be representative of, what the turbulent structure we see, is in the sort of, hot phase of the halo, right? In other words, you're sort of assuming that the cool gas kinematics in some sense have to trace what's going on in the hot phase. So we kind of picked velocity normalizations, and sort of structure functions based on that. But yeah.
Okay, for the turbulence and the bulk motion.
Well, no, we didn't include bulk flows. So that's a
Okay.
fair point. That's actually one of the reasons I think the best way to do this is going to be by using something like Gibble, right? Or, there are other high resolution halo simulations where there you should actually have the correct bulk flow as well as, some estimate of the internal kinematics. And I think that's going to be the correct way to do this. If you really want to compare sort of apples to observations.
Thank you.
All right, our last question from Bo.
Hi, it's actually Tom Quinn from University of Washington. This is really great stuff. Thank you for the talk. I was wondering about the large clouds. In your simulations, do they have any internal substructure? In your sort of cloudlet model, comparison with the observations, it looks like you were assuming homogeneous, but are they essentially concentrated? Do they have any self-gravity? Are they subject to self-gravitational collapse?
Yeah, so this is a great question. I'll deal with the last part first because it's the easiest. None of these things are genes unstable. They're too diffuse, and they have too high of internal turbulent velocity dispersions. That said, right, the fact that they have these large internal velocity dispersions means that indeed they're certainly not uniform. And actually, that's probably the biggest weakness of the Cloudflex model right now, is that we haven't included a way to sort of capture density distributions within a single cloud complex. It's in a sense more true to the sort of misty, really small cloudlet model to have the densities be more similar, because one of the predictions of that kind of model is that the smaller the scale of the clouds, the more quickly they can, reach pressure equilibrium with the background. So there you have a sort of reason to think they should be a certain density. But the larger scale structures, and certainly the ones that we see, the large scale structures we see in our outflow models, they have a ton of internal density structure. You can definitely get like higher density and lower density regions. And that is certainly a complication that one thing I didn't show is that one of the things I would really like to do as a sort of another application is compare kind of Cloudflex predictions to like Siegel style model predictions to see like where we might be off, because in Siegels we can resolve down to very, very small masses and scales, and that actually I think is one of the things that may be an issue, but it's probably a bigger issue in outflows than it is in the sort of halo scale small structures. But.
Thank you.
Okay, so thanks everybody for sticking around, and thank you, Evan, for this like really great talk, and your fabulous videos and visuals are really lovely. And for everyone else, the next iteration talk series will be on the 27th. The website has the title and abstract, which I don't have right in front of me, so but we hope to see you then, and have a great Thursday.
Hey, everyone.